Alright, so this video we're going to continue our analysis of circuit diagrams and discuss Ohm's Law. Thus far, hopefully we've learned to be able to look at a circuit diagram, see how the resistors are connected, and be able to use series or parallel connections to figure out the total resistance of a circuit. And what we saw, of course, was resistors in series add like normal. Every resistor connected in series gets added up together, whereas for parallel, it's the reciprocals. 1 over the parallel resistance is 1 over R1 plus 1 over R2 and so on. And so we use these two equations in conjunction with each other to be able to reduce circuits from more complex circuits down to equivalent circuits, which are much more simple. And once we get down to a circuit that just has one resistor in it, we could then figure out its total resistance. Well, Ohm's law, which is V equals IR, again, it gives us the relationship between the voltage of a circuit, the current, and the resistance, can be applied to the circuit to be able to calculate things that we may want to know. For instance, given a circuit, and let's say we've collapsed the circuit down into one total resistance, and of course we've got the voltage. Well, one thing I may want to figure out is what is the current running through the circuit. So of course I'd use V equals IR. I'd calculate it for I is V over R, and I'd plug my numbers in and I'd get my answer. And what this would tell me is that due to this source and the total resistance of the circuit, there is some current which flows out of the source and flows around the circuit, getting back to the voltage source again. So that may be one thing we want to do. Given a circuit, I want to know what is the total current which flows through the circuit. But I may want to do more than that too. Perhaps I have a circuit which is more complicated, like this, for some R1 and some R2. And maybe I want to find out what is the current in resistor 1. That is, how much of this current hits that resistor. And then how much current maybe hits the second resistor. Or maybe I want to say, when the current flows through a resistor, of course, what the resistor does is it uses up some voltage. It drops the voltage as if it's using power. It drops the voltage so that of the total amount of voltage of your circuit, some of it is used by the first resistor and the rest is used by the second. And so maybe I'd like to find out how much voltage is dropped by the first resistor, or how much voltage is dropped by the second. These are the types of questions I may want to ask about a circuit. I want to analyze this circuit and figure out everything I can about it, because maybe what I'd like to do is I have an electronic circuit already sitting there and I want to add something to it. And in order to add this thing to the circuit, I know that the total current which is going to flow into the thing I want to add has to be a certain number. So I want to analyze the circuit and see, okay, if I were to try to add it in here, well, is the current which is flowing to this point, is that sufficient for the addition I'm trying to make? Or is it too high? And if it's too high, can I stick a resistor in there to lower it, and so forth? So the question is, of course, how do I go about doing this kind of an analysis? How do I figure out how much current is in a particular resistor, or how much voltage is dropped by a particular resistor? And that's going to be the point of this lecture. So the first thing to note is Ohm's law itself will be the equation we will use for everything. V equals IR is not just for the total circuit. So for instance, if I know the total voltage and the total resistance, I can get the total current. but it also works for individual pieces of the circuit as well. And so, the best way to show this is to take an example. Let's have this example here. Okay, so here's my circuit, and I'd like to calculate a few things. Number one, I'd like to calculate, or call it part A, the total resistance. Part B, the total current. Part C, the current flowing through the 7 ohm resistor. The voltage dropped by the 7 ohm resistor. And the same stuff for the 3. If I could figure all this stuff out, then I know everything there is to know about this particular circuit. So how can I go about doing this? Well, the first two, finding a total resistance and a total current, we already know how to do. So let's show it. Part A, I want to find the total resistance. So I look at my circuit. I have a couple of resistors here. They're connected in series. And so the total resistance is 7 plus 3, which is 10. So I now know the total resistance of my circuit. Part B, how do I find the total current? Well, of course, I use V equals IR. That's Ohm's law, where I is V over R. And if the V I use for this equation is the total voltage of 10, and the R I use is the total resistance of 10, then the current I get of 1 amp must be the total current for the circuit. I mean, that's pretty simplistic and pretty obvious, but it's important to know. When I use Ohm's law and I use total values, then the answer I get is a total value as well. So given the total voltage of 10, and then I've already calculated the total resistance to be 10 as well, just by the numbers I've chosen, then I'm using total voltage and total resistance to get total current. What about the rest? Let me redraw it, and I'll show you kind of the format I'm going to use for our questions. When I give you a question like this, either on homework or on a test or things like this, generally speaking, what I'm going to do is I'm going to give the circuit, and then I'm going to have a little table of values, which says, for each resistor, here's the 7, here's the 3, I want to know the current and the voltage for that resistor. This is just a nice, easy way of asking the same thing I asked here for these things here, except instead of having individual parts and list it all out, you just fill in the table and you basically give the same answers. Okay, so we already know from part A and B that the total resistance is 10 and the total current is 1. I calculated that before. Now I want to continue. So how can I find the values of individual resistors? I'm going to use the same equation. V equals IR not only works for the total circuit, but it works for the individual pieces of the circuit as well. So if, for instance, I'm looking for the 7 ohm resistor, then the voltage dropped by the 7 ohm resistor is the current which flows through that resistor times that resistor's value. And of course the same would hold true for the 3. The voltage dropped by the 3 ohm resistor is the current which hits the 3 ohm resistor times its resistance. So this is good. I don't need a new equation. I just use the same equation I used for the total values, only now I'm looking at specific parts of the circuit. But again, I'm stuck here because I basically have two unknowns. Let's say I'm looking at the 7 ohm resistor. Well, I know R7 is 7, but I don't know V and I don't know I. Those are the two things I'm trying to calculate. So I have two unknowns in that equation. So that means I must need something else to help me solve this problem. And the thing I need are a set of rules about how voltage and current act on resistors, depending if those resistors are in series or parallel. And so here are your rules. We'll talk series first. If we have resistors in series, like this, we have the 7 and the 3, they're connected in series, so this would count. If we have resistors connected in series, then the first thing to know is that the current is the same in each resistor. Okay? And of course, this makes sense. If we have some current flowing out of our power source, well, that current has to hit the 3, and then coming out of the 3, it then has to hit the 3. I mean, coming out of the 7, it has to hit the 7 first, and then it comes out of the 7, and then it has to hit the 3, and then keeps on going until it reaches the beginning of the circuit again. So the current is the same on the 7 and the 3. It has nowhere to go. It must flow through both. So if you know the current on the 7, then you know the current on the 3. They're the same value. Okay. The other thing to know is that the voltage is different on each. And what this says is, let's say I want to know how much voltage is dropped by the 7 ohm resistor. Well, that's going to be the current which hits it times its resistance. And then I want to say the same thing for the voltage on the 3. Well, it's whatever current hits it times its resistance. Well, if both of them have the same current, I, but they have different values of resistance, then obviously they're going to have different values of voltage dropped. If I is the same on 7 and 3, call it 1, then 1 times 7 is 7, and 1 times 3 is 3. They have different voltages. And so those are the two rules there. If you have a series connection of resistors, then the current which flows through those resistors is the same on all of them, but the voltage dropped is different for all of them. Okay, what about for parallel? If we have two resistors connected in parallel, believe it or not, it's the exact opposite. The current is different for each. But the voltage is the same. And so if we have an example like this, here's parallel. Call this 7 and call this 3. Then let's look at the current. The current coming out of the power source is whatever it is, but then it reaches this point where it splits. Some goes to 7, some goes to 3. Well, the way the current works for these wires is that the current wants to choose the path of least resistance. So you're going to get way more current flowing through the 3 than you would through the 7. So the 7 ohm resistor is going to feel a different current than the 3 ohm resistor would. That's why the current is different on those two resistors in parallel. The second part says that the voltage dropped is the same. And what this is saying is, if you look, let's say, at the 7 ohm resistor, and again you would use V equals IR for the 7, and V equals IR for the 3, the I is different for both, and the R is different for both, and the way they change is very special. The I will be different on each one of these resistors such that when you multiply it times its resistance, you get the same number as the other branch. So the V dropped by 7 must be equal by law, by rule, to the V dropped by the 3. And the way that happens is by modifying what I is used for the 7 and what I is used for the 3. So think about it this way. Let's say I do V equals IR on the 3. Let's let I be 1 for the 3 ohm resistor. Let's just say I happen to know that. So the voltage drop by the 3 ohm resistor is 1 times 3, which is 3. And now I look at the 7. Pretend I don't know what current is there. Somehow I knew what was on 3, but I know it must be different on 7. But what do I know? I know that because the 7 and the 3 are in parallel, whatever voltage was dropped by the 3, the other resistor must also drop 3. So I would know this guy has a V of 3. I know the resistance is 7. I know the V is 3. I could calculate what I must be to let that happen. And that's what V is the same for each resistor in parallel. If you have a parallel connection of two resistors, whatever voltage is dropped by one is the same voltage which is dropped by the other. Okay? Final little things to go with these rules. Continuing with what I just said with the parallel, not only do they drop the same voltage as each other, so let's say 3 and 3, but it's also the same as if you were to take this parallel connection and you replace it by a single resistor instead. So you add them up in parallel and get an answer. Whatever the voltage is by this guy, that's the voltage which is on those guys. So that would be 3 as well. So this is a very good thing to help you analyze the circuit. If you have a parallel branch and you want to know how much voltage is dropped by each resistor, well, forget about the parallel part. Add them together in parallel and get a single resistor out of it. You now know the parallel resistance. Then, whatever current comes into that resistor times the resistance, this parallel resistance, gives you the voltage dropped by that parallel piece. Let's say it's 5. I now know it's 5. What can I do with that information? Go back to the parallel part of it before you combine them. Now that you know the whole parallel system was 5, each branch is now 5. Because that's what it means. V is the same. The total resistance in parallel, that gives you a total voltage dropped by that parallel thing. Whatever that total voltage is, that's the voltage which is dropped by each branch of the parallel system. What about for series? What's the important thing here? I say V is different for each resistor, which meant the 7 is going to drop different than the 3 would drop, the voltage. But one thing we do know about it is that if you add up all the voltage drops across a resistor, all the way around, you better get the total voltage of the system. So if you have a circuit which has 10 volts, battery, and you have two resistors like I do here, a 7 and a 3, well, whatever voltage is dropped by the 7 plus whatever voltage is dropped by the 3 must be equal to the total voltage of the circuit, which I know is 10. So this is going to help me when I try to figure out some of these numbers. If I don't know either voltage drop, but I know the sum must add up to 10, then if I could figure one of them, that'll give me the other. So all of that is theory. Let's look at the example, because the example will make it clear. Here's my 7. Oops. Here's my 3. And again, I knew the total resistance turned out to be 10, and the total current turned out to be 1. And here is the table I want to fill out. All right. So what do I have? I have two resistors in series. And so I know whatever current is on the 7 is the same as the current on the 3. What current is hitting the 7? Well, it must be the total current of the circuit. I calculated the total current to be 1. So coming out of the battery is 1. It comes in, it hits the 7. It has nowhere to go. It doesn't split. So all 1 amp must be hitting the 7. Thus, the current on 7 is 1. I'll make it in blue. And then by the rule of series, whatever the current is on the 7, it must be the same current on the 3, so the 3 also has 1. And of course, we could see it quite clearly. The 1 comes in, hits the 7, leaves the 7, and then goes into the 3 and leaves the 3. At no point did that 1 get split into two pieces. There's no parallel set anywhere. The 1 came in, and it must go straight through both of them. Thus, each resistor feels 1 amp of current. All right, that's good. What else can I do? Well, now, this is the good thing about setting up a table that looks like this. I don't have to worry about anything else. If I have two pieces of a row, the third piece comes for free. Remember, V equals IR. So if I want the V for 7, I take the I of 7 times the R of 7. So 1 times 7 is 7. And again, for the 3, I've got the I and the R, so to get to V, I take 1 times 3 is 3. And now I'm done. There's my answer. Now what I could have done was use the rule for series voltages and say each resistor is going to feel a different voltage drop. And what do I know? The total voltage drop, if you add them all up, must be equal to the total voltage of the circuit. Does this match? Well, I have 7 plus 3 is 10. Is the total voltage of the circuit 10? It is. So it matches. That's just a little check. But that's the hint. Anytime you have a table and you have two pieces, so let's say I knew this was 2 and this was 4, this was 3 and this was 2, then I could get the third piece of each row easily from V equals IR. So this one is I equals V over R. So 4 over 2 is 2. And for this row here, I've got V equals IR, I times R, 2 times 3 is 6. And so it's easy to fill in the third piece if you have the other two. You don't even have to think about any of the rules or anything. You just fill it out. You use V equals IR to get the last number. For the first pieces, if you don't have 2 out of the 3, that's when you use your rules to try to figure out what you can. Let's do another example, this time with a parallel piece. So let's say I have this. And I'll do a big version. Let's say 3, 6, 12. And again, I want to fill out this table. So, given a problem like this, I have a circuit. I want to fill out the rest of the values of this table. First thing I always do is I calculate the total resistance. So, I see the 3, the 6, and the 12 are all in parallel. So 1 over R parallel is 1 over 3 plus 1 over 6 plus 1 over 12. All right, I have to get common denominator. 12 is a common denominator, so that's 4 over 12 plus 2 over 12 plus 1 over 12, which is 7 over 12. But that's 1 over R parallel, thus R parallel 12 over 7. What else do I want to do? Total current. I now know the total resistance of my circuit. So V equals IR tells me that I is V over R, which is 10 over 12 over 7, which is 70 over 12, which is 35 over 6. Okay. Of course, you could get a decimal here if you want, but I'm just going to use this fraction. So every time I have an Ohm's Law problem, I always do these two steps. Even though it didn't ask me to do it in the problem, I'm still going to do it because likely I'm going to need all this information at some point. Now we want to start thinking about the problem. What do I have? Do I have series or parallel? Or both? In this case, I have all a bunch of parallel. So I start thinking about my rules. My rules say each one of these resistors is going to have a different current. Because, of course, more current wants to go to the 3 than wants to go to the 12. It's easier to pass through. So they're going to all have different currents. But one thing I know is that the voltage on the 12 is the same as the voltage on the 6, and that's the same as the voltage on the 3. Okay? So if I could get one of the voltages, I'll know all three of them. How can I get one of the voltages? Well, if I knew the current on one of them, I could get its voltage, but I don't know that. What else can I do? I could use the fact that if instead of this circuit, I were to combine this parallel piece to make the circuit look like this, where this is R parallel, that's R parallel. If I could figure out the voltage on R parallel, that must be the same as the voltage on each one of these branches. That's the rule of voltage for parallel. So how can I find the voltage on R parallel? There's two ways of doing this. First way is I could say the voltage parallel is I on the parallel piece times R on the parallel piece. Well, I know I just found it, 35 over 6. What about R? Do I know R parallel? Yeah, it's 12 over 7. Okay, so multiply these out. 6 and 12 makes this a 2. 2 times 35 is 70. 70 over 7 is 10. I now know the voltage drop by the total parallel piece is 10, and thus I know every branch of the parallel drops 10. So these are all 10. Now, before I go on, there's a second way of doing it, which is easier. Notice this circuit I drew here. This circuit is simple. It's just got one resistor in it and a voltage source. And what rule do I know? If you add up all the voltage drops all the way around the circuit, it must be the same as the total voltage of the circuit. Well, if I only have one resistor, then the voltage drop by that one resistor must be the total voltage. So I know without doing the math, without doing V equals IR, if there's just one resistor, his voltage is whatever the voltage source is, 10. So I could have just stuck the 10 in from the beginning. Either way, they both work, and whichever comes to your mind, that's the one you should work with. But either way, we now have all the voltages. Now, how do I find the I's? Well, easy. For each row, if you know 2 out of the 3, you use V equals IR. And V equals IR tells you I is V over R. So I have 10 over 3 for this guy. I've got 10 over 6, which is 5 over 3 for this guy. And I know 10 over 12, which is 5 over 6 for that one. And again, if you're using a calculator, you'll have decimals for this. I don't have a calculator. I don't use them usually. And so I'm using a bunch of fractions. But I'm now done the problem. Once I got the voltages, the rest is easy because you just use V equals IR on each row individually. But now you can see, when you have a circuit that's series stuff, you use series rules to help you. When you have a circuit that has parallel stuff, you use the parallel rules. Now, obviously, we're going to have more and more complicated circuits which have a combination of both series and parallel. So we're going to be combining rules as we go. For instance, what if this branch had another resistor in it right here? I'll make it in yellow so it's easier to see. A 4. Well, now this branch is a series branch. And so while it's true that the 3 and the 12 have the same voltage, this middle branch with 6 and 4 add up to 10, but the 6 and the 4 individually are not 10, they add up to 10. So I'd have to do a little bit more work to figure out how much of that 10 is dropped by the 6 and how much of it is dropped by the 4. And as we go on, I'll continue to show you how to do that kind of stuff too. But for now, these are the more simplified, fundamental type problems. Can you work with parallel rules? Can you work with series rules? In a little bit, we're going to work on the more complex where we combine them. So that's what you can expect next. I will work on a video doing example problems where I show you exactly how to do this with the more complicated circuits included. And we will continue practicing to make sure we understand this clearly, because this is where some true analysis really starts. Having the series and parallel resistor stuff, that's a tool that we're going to use to do analysis. Now we're doing analysis. We're looking at a circuit and we're looking at parts of the circuit and we're saying how much current is in this part. Or given the circuit is like this, if I were to stick a light bulb right here, call it a resistor, how much current will flow through that light bulb, and thus what's the power of the light bulb? What wattage? Is it a 100-watt light bulb? Is it a 50-watt light bulb? I know that by knowing how much current is flowing through and how much voltage is dropped by that resistor. That's what these things allow us to do. So that's what you can look forward to next. For now, practice this stuff. Of course, practice the practice problems on Canvas. And until next time.